And in fact, one of the things in today's talk that I'm really going to focus on is talking about techniques in perspective. So thinking about the fact that we can't we can't do this electrochemistry in isolation. We have to think about it in the broader system with other techniques, but also we need to think about it when we're thinking about corrosion. We're not thinking about an ideal system. We're thinking about a system that has complexities which might not happen in other types of sort of electrochemistry fields. So I'm going to sort of touch on all of those points in particular. And in fact, today in the examples I'm going to give, I actually am going to talk more about examples from literature because I found some lovely examples that I think really illustrate the point. There isn't a significant expected knowledge on the topic of electrochemistry, but I hope to really encourage, and perhaps some people will want to then explore some of these ideas in their own work. So that's sort of my motivation for today's webinar. But before we start and we delve into the electrochemical side, I want to think a little bit about the history of corrosion measurement and where it came from. Because the reality is that we talk about its ubiquitous nature today. We talk about the fact that it's, it costs all this money. But the reality is people have been studying corrosion for a long time. But our emphasis in terms of what we're studying is changing, and our goals in terms of understanding it have changed. So the core of corrosion testing at the start was really about understanding how the material was changing in terms of loss of material. It wasn't necessarily focused on what was happening, but it was on sort of whether or not the material was going to remain sufficiently robust. And in all honesty, that continues to be a genuine concern and a way that we need to consider to think about all of our problems, because that is the industrially relevant question. Is the material going to hold up for the length of time that we need it to? So that sentiment is very much the foundation behind immersion corrosion testing, right? Where we take a sample, we subject it to the conditions, and then we look at what happens afterwards. And in particular, what we generally do is we look at how much that material changes in terms of generally mass. So the sort of traditional way of quantifying this is corrosion rate. And so you can read lots about it in the ASTM standard, which really provides a really nice baseline and guidance in terms of thinking about this. And what it is it's the loss of mass. But the challenges lie in the sort of detail in this expression, because we're going to normalize it based on surface area, time of exposure, and density of the material. And the challenges at that point are, in fact, well, is the mass loss where does our measurement error lie? But is this a linear behavior? And moreover, the surface area we know is evolving. That you can see that in and of itself. So what surface area do you use? And then there's always the challenge that has your density changed? So what density are you using? And so corrosion rate provides us this really great basal analysis for having sort of this foundation of what's happening. But the reality is that it doesn't tell us very much about the chemistry, the mechanisms. And so my group is founded on this idea that if we want to solve a problem, we need to understand it. And so whilst I am very pleased in most cases to look at this approach, we need more, right? We need to add techniques and approaches to give us a bigger picture. But the other interesting thing about this analysis, right, is we're assuming homogeneity. We're assuming that the corrosion is uniform across all of our system. And that is one of the points that can very much get us into a bit of trouble. And so that's kind of where I'm going to switch gears and move away from sort of the historical. But what I wanted to start with was highlighting the fact that I think most of the audience is familiar with this idea that corrosion is generally, whilst an enormous umbrella, it's subdivided into two smaller umbrellas. General, i.e. sort of this generic behavior that's relatively homogeneous, and localized. And the reality is localized is now another enormous umbrella term for many, many types of corrosion. And so for today's talk, I'm only going to focus on general corrosion. And there's a lot of reasons for that, but I feel that localized corrosion, we'd be doing lots of little bits and pieces, and I'm not sure that it would have. So maybe in a future webinar. But today we're going to talk about general corrosion. And what I want to spend time talking about is particularly techniques that are not only just suited to understanding corrosion, but are commonly found in the literature and can be quite useful, but also ones that people might be inspired to sort of give it a go. That said, as I sort of go through, I will offer some cautions that go with the techniques. And it's not going to be an academic lecture with all of the detail of the derivations and such, but I will sort of make some references to that to sort of provide some baseline understanding. So I very much hope that it will encourage and inspire people to think a little bit more broadly about the types of experiments they do. So with that, I'm going to jump right in and talk about the crux, if you will, of our sort of electrochemical measurement, and that's open circuit potential. So when we have a metal, so in this case I've shown iron because it's one of our favorite things, we have an oxidation reaction, right, where the iron 2+ is released from solution and the electrons then can be subsequently reduced as part of the cathodic reaction. So I've shown the two here, and what we have in effect is that when we have the rate of oxidation and the rate of reduction, so here I've modeled them with each with one individual reaction, at the point in which those rates are equal, we call it an electrochemical equilibrium. And that is the point at which we would say we are at sort of our open circuit potential. And so, as I said, this is the basis, and here's why. So open circuit potential is one of the most natural ways to segue from that immersion test to other electrochemical techniques. And the reason for that is because you're not applying any potential or any current for that matter. What you're doing is you're tracing. You are registering what is happening without any input from, say, a potentiostat. Of course, the system itself is providing input, and that's what's causing the changes to happen. So I've picked an example from the Nezik group that was published in 2011, and I hope that it will illustrate a bit about the power you can have with this technique, particularly when you want to understand a system where the environment around you is dynamic. So in this lovely example, what they've done is they've had a 3-stage experiment where the first stage they've introduced carbon dioxide, and then after this predetermined time they've introduced some H2S, and after which they've decided no more H2S, and they've introduced only CO2 from there on out. Now CO2 was introduced throughout, and this is, I am cherry picking a little bit. The paper's got obviously some other experiments in, but I think this one will illustrate the point. So the question is what's happening during this process? Because you can see the blue line following the open circuit potential, you can see that there is a tremendous change happening during this process. So please pardon my simplified cartoons, but I'm hoping that what they will do is they will illustrate some of the things that are happening to help visualize. So in the first instance, when you introduce CO2, I'm imagining oversimplification where you have oxidation of your iron and so on and so forth, and you're creating this system. But what becomes interesting at that point is you introduce H2S, at which point the authors describe they see the increase in the potential, and they ascribe this increase in potential as a result of the formation of sort of an iron sulfide layer. So you might have seen it appear in the last step. We'll do that again. So the iron sulfide layer is coming out on the surface, at which point they turned off their H2S, no more. They see a small jump, which perhaps can be attributed to something like iron carbonate forming on the surface as it becomes preferential when the H2S is no longer available. Perhaps, but what's more interesting is they see an enormous decay in their potential, and that decay they attribute sort of as a hypothesis to the removal of that layer that they just created. Okay, so this is the jumping off point. This provides us a tremendous amount of information. We are making suppositions at this point, but in fact, what we're doing is we're saying we see the changes happening. How can we now probe them to confirm our assertions? And so the answer that they first take in that first leap is they talk about potentially dynamic polarization. So this is sort of one of the most, in some ways, straightforward experiments. So at the end of each stage of their experiment, they decided to run this. So the way it works is they're going to start at their open circuit potential, which obviously is different depending on the stage they're at. And they are going to introduce first a cathodic scan, and then they're going to allow the system to return to open circuit, and then they're going to introduce an anodic scan. So in effect, they're going to apply a potential and record the current. And so they ran 3 independent experiments. I think that's important to point out. running only to the completion of the stage, since this particular type of scan can, of course, create a history in the sample, therefore making it sort of unable to follow the time series. But what's lovely is, so in that cathodic scan, what we have is the introduction of electrons, which allow the reductions to take place. And so the rate of reduction in this region is going to be significantly more significant than the rate of oxidation. And by contrast, when we move to the anodic scan, we sort of have the reverse situation where our rate of oxidation is going to be significantly larger than our rate of reduction. Okay. So with that in mind, right, we've got these three stages. And so we're talking about what's happening at each stage, and we're talking about what's happening with respect to these conditions under which we're encouraging, in the cathodic scan, right, we're encouraging one set of reactions. By contrast, we're encouraging a different set of reactions when we employ the anodic scan. And so there's a number of things potentially to take away from this. So you have the same graphic on the left of your screen showing basically the open circuit potential. And then on the right, what you now have is you have these potentially dynamic polarization curves. And so what becomes interesting is starting to think about these curves in the context of what we were just discussing, what the authors in this case believe is happening. And so the first thing that's quite clear to notice is that, so we have enumerated stage 1, stage 2, and stage 3, is that stage 2 looks different, right? And you can actually see that leap in the potential. And so that's not at all surprising, given what we have observed from the previous scan. So that's sort of comforting, I suppose. But what the authors find particularly interesting, and as do I, is that the cathodic scan is not particularly affected by the formation of this layer. So stage 1 and stage 3 look quite similar, right? And so they're asserting that, well, they've removed this layer, and so we're kind of back to the same bare metal. So not so surprising, but the cathodic scan looking quite similar. When you have this layer, is interesting because it suggests that that cathodic reaction is not being strongly influenced by the formation of the layer. But by contrast, they suggest that the anodic scan is somewhat more influenced. And as such, we can actually start to think about the nature of that layer. So if the cathodic reaction is happening, i.e. electron transport is occurring, but we don't believe that the oxidation reaction is happening quite as smoothly, well, that's telling us something about the porosity and the nature of that layer. So they sort of assert that from literature that this corroborates findings regarding the nature of an iron sulfide layer, particularly sometimes noted as being an inductor. So up until this point, we've only talked about a very small number of experiments. In fact, we talked about one very long experiment, right, that they ran for 27 hours. And we talked about 3 very brief experiments, but already we're getting quite a good sense of what's happening in our system without having done anything terribly fancy, for that matter. But what I want to do now is what I was starting to talk about at the beginning, which is putting the measurements into context. Because when we're doing electrochemistry, we are focusing very much on that interface, what's happening, in this case, the liquid and solid interface, and maybe we probe a little bit into the diffusion layer and so on and so forth. But the reality is that the system extends further into the bulk material of the metal. There can be impacts in some instances, and in other cases, into the liquid. And so that's this kind of holistic view very much allows us to, again, start completing that picture. And so interestingly, later in the paper, in reference to something a slightly different point, but really illustrates the fact that they observe that the iron-iron concentration in the bulk of the solution is changing, again, at the end of these 3 stages. And most notably, to see a decrease in that concentration when they sort of are at the end of stage 2, when they believe that they have that iron sulfide layer formed, i.e. those iron ions have gone somewhere. And so, but by the conclusion of stage 3, where it looks very much like that iron sulfide layer has been removed, all of a sudden you also are seeing an increase in the iron-ion concentration in the bulk. So this is starting to, in fact, also close the mass balance, right? Because we know that we must have those iron ions somewhere, and so this is giving some sense of where they might be. So without this, we can continue to have an idea of what's happening, but the reality is that it's the pieces that go together. So they didn't stop there. They've highlighted a whole range of other techniques, and One of the things that's particularly interesting is that they did SEM imaging on their materials at the conclusion of every stage. And one of their findings was, in fact, for this particular set of experiments, that none of the samples look demonstrably different. And moreover, they all kind of show active dissolution, and EDX didn't really indicate any sulfur in that intermediate sample, really only iron and carbon, which is somewhat challenging. And so if they'd only looked at that surface analysis, they might have been surprised, right, that nothing had happened with the introduction of H2S. So, but in fact, further inspection using XPS has highlighted that there might be some indications of formation of iron carbonate and iron sulfides. But this again points to this necessity that electrochemistry, even a very simple experiment, in fact, can help us understand quite clearly what might be happening. So it's an interesting way of viewing how much we can get from actually very limited and very simple experiments. And so at this point, maybe what you've noticed is that I haven't really focused. I was quite quick, and I went over when I introduced this graph and the experiment. I ignored the red squares, the corrosion rate squares. But I don't want to ignore it entirely, because I think that it's quite important for me to take a minute and point out a little bit about how those calculations are made, and to offer some cautions to people who are maybe new to this field and thinking about using this as a methodology. So the application of corrosion rate, we're going to step back to how we get to the point where we can make this plot, is a result of basically at short time intervals making perturbations, about very, very small ones that are expected to be reversible, where basically we're perturbing our system in terms of the potential. And again, we're applying the potential and recording a current. And the idea here is that we expect that if we make this very small perturbation in the potential and record the current, we'll have a relatively linear behavior because it's sort of a small differential space. And we can essentially use Ohm's law, where we can determine then what is the resistance of the system at that point in time. And if we do this at regular time intervals, then we can sort of create a figure that sort of highlights how the resistance of the system is varying. And in fact, we often normalize it based on surface area. But again, just as I said at the beginning about the bulk material situation, that also has the challenge that your surface area is evolving and how you decide to model that. So there are some suggestions. Again, I'll plug the ASTM guidelines if you want to know more. That's a really good place to start. But what you're still wondering is how we got to corrosion rate. And I realize that there's more math and explanation than you probably need on this screen. But what I want to take a minute to do is just explain how you've gotten there. So thus far, I have explained how you get those small resistance measurements. And so in the center of the screen, you'll see an expression for the corrosion current, so I core. And that's a function of this, the area normalized resistance. And it's also a function of another sort of constant called the Stern-Geary coefficient. And this is where things sometimes can become a bit nerve-wracking because those potentially dynamic polarizations that were made are often very, very good and useful. And one of the reasons they're often used is because we try to extrapolate more information out of them. So a lot of the analysis that I discussed about the ones previously done, I discussed qualitative assessments. But one of the things often is done is we try to reduce the phenomena occurring to try to actually extrapolate, again, numbers. Numbers are always good. So what's happening in that black sort of somewhat noisy example, which I've drawn, is actually the current response, right? And the current response is a net response. It's the combination of the anodic and the cathodic. But there's a point at which, as I introduced way back at the open circuit potential, that net becomes zero. But this is riding on a range of assumptions because if you remember, I talked about that, where we said that there was a single oxidation reaction and a single reduction reaction, and at which point those two become equal. We reach that point, right? Well, the challenge is that these things are not always the case. And we use this basically linearization of each of these phenomena as a way to determine what the angle is. So I realize that I'm blowing through the math here, and my sincerest apologies, but what I really want to get to are the cautions that need to go with this technique. So we don't have time to go through the math, but what I do have time to do is to remind people that the application of the Stern-Geary coefficient in that form requires that the system is kinetically controlled. So everything has been limited. And so if you have any diffusion controlled systems, you have to modify it. And this can mean one of your reactions is diffusion controlled, where, okay, you can quite quickly figure out how to simplify the expression perhaps. But if you have the case where you have a mixed control, where essentially the order of magnitude of the diffusion and the kinetics are consistent, then in fact the situation is far more complicated in terms of how you model it. And the utility then in modeling it is not necessarily as obvious. But moreover, so you might say, okay, well, I have linearity near, so I must have kinetically controlled. So the other caveat is that you need to be quite careful that this sort of derivation also doesn't account for such issues as electrolytic resistance. But moreover, it also doesn't deal with competing reactions. So we're assuming for a very, very simple system. And so my intention is not to put you off, but is to make sure that if you're using this technique, is that you're thinking very, very carefully about the kinetics and the mass transfer of your system, but also about what reactions might be happening and what assumptions you might be making. But at the end of the day, if you go ahead and make that plot of corrosion rate, what you might find is that, in fact, it does give you something to hold on to. It gives you this number and you say, but corrosion's getting better. But it doesn't give you the meaning that sort of we just talked through just by using an approach, which in fact was generated using essentially very, very similar data. So I would advocate that you use caution and certainly get more information if that's the approach you want to take. Okay, so I talked about that enough, and I do want to get to two other examples, and I know that the next example I have is going to be a little bit complicated for those of you who are not familiar with impedance spectroscopy. But I want to move on to it because it's one of the most common things that can be seen in corrosion literature in terms of understanding the formation of layers. And so I want to take the time to do that to make sure that we have a little bit of understanding. But what's beautiful about this example, so this paper was written by Gao and published in Corrosion Science in 2011, is they start off just where I left off, which is about plotting that resistance. So what's lovely in this experiment is they're looking at X65 steel, and they're looking at what happens when they're in sort of a seawater environment and at different temperatures. And what they see is that that resistance basically goes through three regions. It goes through an initial region where you essentially have relatively constant but relatively low resistance. Then you see a linear increase, and after which there's again another plateau at a higher resistance. And so they see this at 75 degrees and at 90 degrees, and I'm going to highlight the case at 75 degrees. So the question then is, well, what is happening in this system, right? So same sort of process of thought. And so they hypothesized that in that initial period, they do have some sort of layer on their substrate. And so I've highlighted that in light green to sort of illustrate it. And then by the end of the experiment, they don't know what they have, but they know they have more. They know they have an increased resistance, and so that could come from a thickening of the layer. It could come from the formation of a new layer, and in fact, the formation of the new layer could be quite interesting because it might in fact be a multitude of layers, and so on and so forth. But finally, it could also just be entirely new species. So this poses three hypotheses, but it poses a significant challenge. And so the way that they've chosen to try to test what's happening is to use impedance spectroscopy. And so it's a lovely way of trying to improve our understanding of what's happening in our system. So I recognize that today it's going to be a bit of a black box, my explanation, but I hope it gives you enough understanding to understand sort of how the analysis happens and how it can be useful in other applications. So with that, you can see at the top, the red curve, which is nicely going along, is the applied potential. So it's a sinusoidal wave. And what we're doing is we're applying that and we're measuring the current. Sounds familiar. What's nice is we're looking for changes in amplitude, phase shift, and so on. So it's a perturbation technique. But what is different about this is we start at a high frequency, and then we work our way down to lower and lower frequencies. And in effect, the challenges, is that we're dealing with a time lapse. So we are employing changes in frequency with time, but we have the challenge that corrosion is not necessarily always a stable phenomenon. So we have to be sure when employing this technique that we have a reasonable idea that we're at some form of steady state. And I say that with lots of, sort of fuzzy words to go around it. And the reason I say that is because with corrosion, as I said at the very beginning, it's not an ideal system. We don't have this ability to just create a perfect ideal world. So we do have to work. And so there are other cautions associated with making impedance measurements. And anyone who's interested in this, I would very strongly encourage you to read up on it. But we do have to make some concessions. So the number one issue is making sure that you're at a steady state, or that during your measurement you feel that you're at a sufficiently steady state, that you will be able, that we're not going to be concerned about decoupling what's happening as a function of time versus what's happening as a function of frequency. So with that, I'd like to sort of explain with a very basic model what's happening to allow interpretation of the data that I'm going to show. So for today's example, I'm only going to talk about two types of components in a circuit. So I'm just going to talk about resistors and capacitors. So in my circuit here, I have two. So I have impedance noted with a Z. And so I've got a resistive component and I've got a capacitive component. And so my resistive component is plotted on the x-axis, which is the real axis. And by contrast, the contribution from the impedance, from the capacitance is imaginary. And so we have that contribution on the y-axis. And so what we find at very high frequencies, so that's sort of the black sinusoidal lines, and where the red, and if you look at the red dot on the figure on your right, what we see is our electrons preferentially move towards our capacitor under these conditions. However, as that frequency becomes very high, in fact, the impedance is effectively zero. But of course, this is only one extreme, and we're going to move our frequency to lower. And as we do that, so that's sort of the blue example, we see that some of our electrons will travel in one arm and some in the other, so some going towards the resistor and others towards the capacitor. So the contribution from the resistance can be observed on the x-axis, the real axis. But now you can see that we're also seeing a really nice contribution coming from the capacitance, and that's in the imaginary, the y. So each one is providing that sort of contribution to the impedance, which we're plotting in this way. And then the final case is when we take our frequency really low, towards zero, and at that point we're going towards the resistor. And again, you can see, so the contribution from the capacitor is effectively zero, but our real continues to increase. So what's actually happening in this system? So the semicircle that we have is what we would expect to see based on this type of circuit. The gap, the diameter of the semicircle is sort of the resistance to charge transfer, and the gap you see between the zero and the start of the semicircle is what we would have as resistance maybe to solution, which I didn't show in this sort of illustration. But hopefully you can sort of see the pieces in this ideal system. And so I've chosen this example because it has a sort of a digestible system that will allow you to sort of make the translation from that simple model. So in this test where they have done it, they've looked at those 3 time points, before, during, and after sort of that resistance change. And what you can see is that they get sort of, they're certainly not semicircles, but they have the flavor of it. And so as time increases, we see the amplitude of the loop increasing, i.e. the impedance in the real direction. And what that implicates is that the resistance to charge transfer is increasing, i.e. the charge transfer process is being held back. So the question now is, what more can we get from this? And the answer is a tremendous amount. So in the first instance, at that early step, before anything is formed, the question is, well, they had hypothesized that they had sort of a layer. And so the goal is to take that physical understanding of what's happening and to translate that into a circuit model. So what can be a challenge in some instances is being uncertain of some finer details. So I am going to jump ahead to the model that they've chosen, but my guess is that they looked at several models. So we have the resistance of the solution, which large or small is something is likely to exist. And then we have that layer, and it will have a resistance and a capacitance. And then the additional component is the resistance to the charge transfer, which we were just discussing, and the capacitance of the double layer. Okay, so I haven't gotten into the details of those, or particularly the exact geometries, But one of the challenges can be deciding what components are in series and in parallel and so forth. But what is important is to think about the physical system and to use that as a methodology for deriving the circuit model. And then to take the circuit model and then to plot it against the fitted data. So that's what you actually can see in that small figure, where the measured is it with black triangles and the fitted is with red circles. And one of the difficulties at this stage can be that with a non-ideal system, the match may not be as ideal as one would hope, right? So you calculate something like the least squares, and you find that in fact the compatibility may not be exactly where it is. But one of, for example, of the things that often comes up is looking at, for example, you may have gone to a frequency that is so low that in fact your system started to become dynamic. You verged too far from steady state. For example, as one of the challenges that comes with corrosion and impedance. So if we go from there and we think about, well, what was happening in that intermediate step? Because we could hypothesize there were all sorts of interesting things happening. And the reality at that point is you might have to draw several circuit models and test them all out. So I'm going to jump ahead in this particular case, and I'm going to guess that perhaps we have a two-layer structure. And so I've illustrated that on the right, sort of that idea that we had some sort of layer, and perhaps the layers changed in thickness, I don't know, but another layer is certainly found on top of it. So again, we'll find that we would have a resistance to our solution, and we'd have a resistance on that new layer, and a capacitance, I should say, and then the same again on the original layer. Now, the resistance and the capacitance doesn't have to be the same as it was at the earlier timestamp. It can evolve. And in some ways, that's one of the things we're looking for, is how that layer may evolve. And then again, we're going to have resistance to charge transfer and capacitance of our double layer. And you can see that the data's in the plot that they provided. It looks like it fits quite nicely. Okay, so what more can you get out of this? And the answer is actually potentially quite a bit. It sort of depends on what else you know. But one of the things the authors point out is that the resistance of the layers is an order of magnitude apart. And in fact, the resistance is so demonstrably different that they hypothesized that the new layer must be thinner than the original layer, or rather than the layer which was originally there, which may have changed thickness. So this poses a very interesting sort of point that you're starting to think about the evolution of the sample and the evolution of those layers. And another thing is sort of looking at that capacitance and how it's evolving. And so that's where it becomes interesting, because we know that we were building, in that intermediate time step, we were building what we think was some sort of, additional resistance, i.e. through a second layer. So the question is, well, how does that change as we reach the sort of final time point? So it would be reasonable to suppose you sort of have the same structure. And so the question becomes then, well, how is that layer actually changing and what's interesting about it? And so they do see some evolution in terms of the resistance and capacitance in the layers individually and comparatively. But the more exciting thing that the authors are drawn to is the fact that it's back to this issue of charge transfer. And so they believe that, in fact, that this significant increase in the resistance to charge transfer is likely related to the fact that that new layer is actually changing in form, perhaps becoming less porous. And so that's where this kind of, again, becomes quite intriguing. So we've moved and we've hypothesized how the layers are changing. We've got an idea, and what's very nice in this particular example is that we are now going to take electrochemistry out and put it with other types of data and analysis. And so in this instance, what they've done is they've actually used some lovely SEM cross-sections and surface analyses, and they can corroborate what they've observed in terms of, first, the formation of an inner layer, they call it, and then you can see sort of a bit about the crystals that are formed in this particular instance. But here's where I think it becomes quite fun, is that they can see the second layer. So I've annotated at the top of their image so you can sort of see how they line up. And in fact, certainly near the top of the image, it does look like that new layer is quite a bit thinner. And of course, they've actually created sort of an artificial edge here to help them observe these behaviors. So that's quite fascinating. And in fact, they've taken a beautiful surface image which highlights the nature of these two layers being demonstrably different. But it's only together, the electrochemical data with this sort of, with these SEM images, they were able to start to really understand the system. And in fact, again, the outer layer now does appear to be thickening a bit. And one of the nice things, they've shown an image from the top, and one can sort of presuppose on the fact that they've only shown one, that it really is changing, and that is quite fascinating. But I would say they've gone one step further, which I think is really lovely. And so they've gone now outside of those bounds and looked at the porosity. And so one of the things that you can look at, in fact, is actually seeing the porosity and how it's evolving. And so they're able to further substantiate what they're seeing in the electrochemical data. So we understand now about how the resistance to charge transfer is changing. We understand all of these details, but we can actually see the porosity evolving from sort of complementary experiments. And so together, actually, this is all forming a really nice story that's quite helpful. But impedance alone wouldn't provide all of this data. Okay, so I have talked your ear off about impedance, and I haven't even talked about measuring or estimating thicknesses or anything like that. But I hope that it's a jumping off point that might excite some of you. And so I do want to take a few minutes now and talk about something my group is doing, though I would say we're doing some of the things I presented before, but something that is not so commonly found in literature, but I hope might be of interest. And this is particularly the use of thermodynamic predictions as a way to understand sequences of reactions that occur in cyclic voltammetry. So this very much is rooted in fundamental science, but the idea is by understanding the sequence of reactions, we have the potential to control basically and push our system into a region that would be particularly useful. So I am going to start by explaining the background of this just so that there's enough understanding. So my PhD student, Kyra Sedransk, is working on this project, and so I want to obviously credit her. So this schematic shows the process, which you can find in post-combustion carbon capture, and actually it's the same technology in natural gas sweetening. But what we're doing here is we introduce a flue gas. It interacts with an amine. The amine then travels from the low temperature region to the high temperature region, where it then releases the CO2, which it had reacted with at the low temperature. So why is this of interest to us? And the answer is, well, this technology is quite advanced, but one of the challenges is the cost of infrastructure and the cost of corrosion maintenance. And so our group has been quite interested for a while in this idea of how can we mitigate corrosion, how can we reduce the cost, and so on and so forth. And so that's the impetus for this project. It's very much entrenched in making the process economically feasible. So the nominal background sort of required to understand is that amines don't behave the same way in the presence of CO2. So primary amines, like the one shown, MEA, react in a sort of a direct capture mechanism, and that's advantageous in some ways. The reaction is quite quick, but it requires a 2-to-1 ratio. So it's not necessarily, it sort of costs more than we would like, and it produces carbamates. By contrast, tertiary amines, which are actually more popular for natural gas sweetening, react in an indirect method. So, but the stoichiometric ratio of 1-to-1 is far more desirable. But what's interesting about this amine is that we produce bicarbonate and carbonate as a part of this process. And so the solution composition is quite dramatically altered. And so one of the nice things about that is that we can find that we can form iron carbonate on the surface. You'll see on the screen an untreated carbon steel, one treated with 5 molar MEA, which in fact is quite actively dissolved. And by contrast, our case with our tertiary amine is covered in a beautiful siderite, which provides an enormous amount of protection against continuing corrosion. So where can we start to understand, because we have MEA and we'd like to work with other amines, how can we understand how these corrosion phenomena occur that we can push our system into a region where we see the same types of protective behaviors? And so one of the things we're doing in this quite fundamental study is trying to understand that with the look towards a very industrial attitude of trying to actually apply it. So the challenge is that thermodynamic predictions are just that. They are only thermodynamic. So there are no kinetics. Thermodynamic data is very limited. And often the extrapolations are, it depends, right? So, and the additional challenge is that making these derivations is a valid sort of an equilibrium condition. And so the result is that they can be quite limiting, but they can be quite helpful in terms of guidance, in terms of what are the sequences of reactions. I'm going to show you a bit about how we use those in the last few minutes. But the last thing that I would say is that the conditions under which you generate your diagram is absolutely essential to understanding whether or not they're applicable for your system. So again, I sort of offer some cautions before jumping in, maybe with 2 feet or head first. Okay, so where does this land us? So one of the things we wanted to look at first was how open circuit potential was different between those two amines when they have CO2 saturation, to try to understand perhaps that's part of the driving force. But in fact, we see that MEA with a pH of approximately 9 when it's fully loaded with CO2 lands firmly in what we would thermodynamically predict as the iron carbonate region. And we don't see any iron carbonate. But by contrast, when we do the same thing with MDEA, which has a slightly higher pH, we do see the formation of these crystals. So this is a 25-degree experiment in an attempt to slow down the kinetics and to try to understand it a bit better. We do see the formation. So the question is, okay, so how can we make MEA do what we want it to do? And the answer is we need to understand it. So the tool that we're using is cyclic voltammetry, which is in effect it's a variation almost on potentiometric measurements. So we're going to essentially introduce a wide sweeping potential, and then we're going to return at the same slope. And then in most cases, we'll repeat this process. And the idea by repeating it is you can actually see the evolution of the materials. What is reversible, what is irreversible, how things compound on one another. So to sort of get to the point of what we're doing is that this is our cyclic voltammogram, where we have no rotation with a dashed line and rotation with a solid line. And what you can see in the first instance is we have iron oxidation. So we have the formation of iron ions. But where this gets interesting, so this is our first step, which we have previously illustrated. Okay, where this gets interesting is what's now happening. So as we move our potential in our CV, what we begin to see is the additional reactions taking place. And what becomes interesting is trying to determine what those are and using those thermodynamic predictions as a methodology for basically providing an undercurrent for what might be happening. And so in this first instance, we believe that this is in fact due to that. This is due to a reaction forming iron carbonate. And one of the things by introducing such variables as rotation, scan rate, temperature, is we're able to elucidate more about which mechanism it might be. And so in this instance, I am going to sort of gloss over it a bit, but we are able to sort of understand that we likely here, due to the rotation in particular is one of the factors, we are likely observing a reaction which is solution-based. And so this again is also contributing to a wide range of research going on, trying to understand these kinds of phenomena about reactions being surface versus solution-based. So if we go from there, because I'm sure you can already see that there's other peaks of interest. So we have this initial reaction where we're forming our oxidation. It reacts with those lovely bicarbonates, and then we form our layer. So iron 2+ now probably doesn't penetrate particularly well. Okay, so it's relatively blocked. So what happens then? And so what you can actually see is that in the case with no rotation, is that there's an additional set of reactions happening. And what's interesting at this point is that it's probably a combination of reactions. So, but moreover, it's probably a conversion of the iron carbonate either to magnetite or hematite directly, and potentially some interconversion. And I'm going to get to that in a minute. But these forward-based, it probably has a multitude of forward-based reactions. And I am saying that with the insight of having seen other pieces of data where we're looking at all these different parameters. But being able to start to elucidate that is quite important in terms of controlling, again, where you sit in terms of what you would like to be forming as a passivation mechanism. And so what becomes interesting is we have now formed this additional layer on top, but it It has perhaps some porosity, we don't know. It may not be as uniform, but what we find on the reverse scan is we see a small but sharper peak, which actually likely is a single reaction. So one of those reactions is returning. And the reason we know that is actually in other experiments where we shift scan rates and temperatures, we're actually able to elucidate the separation amongst these different mechanisms. So we actually can control, depending on where we sit, which things are going in the reverse direction. But it becomes even more interesting because we believe that by doing this, we're changing the nature of that film, certainly on the outside, but perhaps even the inner film at this point, due to those reduction reactions. And so porosity may likely be induced, because one of the unusual things here, as I said, is what we have here is, of course, a net current. But we are seeing overall oxidation, so we're having reformation potentially of iron carbonate in a very unusual place. But again, as a function of all these different parameters, we can actually highlight when we make it and when we don't. And now we suspect, and in fact this is possible due to ion transport through basically what we've created, a somewhat porous layer. So here's sort of a short example to illustrate the role of temperature that it can play in the system. And you can sort of see how we can use it to start to look at activation kinetics in terms of activation barriers. But also one of the things we can do is we can use this type of data to start to also understand actually how much charge is involved and how many molecules in fact are reacting in each of these individual steps. So in one aspect, we're continuing to pursue that, but what you may have also thought about in terms of this presentation is that in fact what I showed was a multi-layer system that perhaps harked back to the example that I was previously presenting about impedance, and so I'm sure with your imaginations you can think about what we're doing at the moment in terms of other ways of characterizing that type of system to better understand how it's evolving. So with that, I've done my best to keep the time. I think I'm probably a little bit on the long side, but I hope that I've taken the time to sort of give you a taster on some of the key ways that we can understand generalized corrosion using electrochemistry, and particularly putting it in the context of using other methods, not just as corroboration, but as a mechanism for piecing the story together, so that we can, in essence, understand so that we can control the system. And I'd like to take this opportunity particularly to acknowledge the two literature examples that I thought really illustrated the use of these techniques beautifully. And of course, my student Samara, who's doing wonderful work with these thermodynamic predictions and all sorts of electrochemical measurements. So with that, it has been my pleasure today to talk about electrochemistry, particularly in the context of corrosion. And I hope that we obviously have a few minutes for questions, but I'm also more than happy to talk about things in the future. So I would say don't hesitate to be in touch and ask questions. So thank you very much.